so part 3, we have a ping pong ball and a bowling ball. I like this problem because I kind of made it a little tricky. So, describe the time interval to stop each. Does one take longer? If so, why? Um, so let's be clear. We exert the same force to stop each. So they have the same momentum, and we're exerting the same force to stop each. So let's be clear. We have the force of the, here's how I'll write this. I will actually use the impulse momentum theorem for the ping pong ball and the bowling ball, and I'm going to compare. And I'm going to use the math and the physics to really compare. So for the bowling ball, I've got the force on the bowling ball times the time on the bowling ball to stop it equals, we end up stopped, and we start with m of the bowling ball times its speed, which is 6. So we'll have it move a positive 6 towards us, and that's fine. And then we're going to say force of the ping pong ball times time of the ping pong ball equals 0 minus mass of the ping pong ball times its v. One small thing. We're told they have the same momentum. So I'm going to call this P. And this is the same P, the same momentum here. So here's the deal. It turns out we're told the same force is used to stop. So the force on the bowling ball is the same as the force on the ping pong ball. So I can just kind of call that F for the sake of this argument. So I'm going to say F times time on the bowling ball ends up being negative of the momentum applied to it. F on the ping pong ball, which is just plain old F, times time acting for the ping pong ball is negative P as well. It's the same momentum and the same force. What did this tell me? The time to stop is the same because we have the same force and P, momentum, so the same time. Let's calculate the momentum of the bowling ball. So the momentum of the bowling ball, here we go. So the momentum of the bowling ball is going to be mass of the bowling ball. Momentum of the bowling ball is going to be mass of the bowling ball times 6, which is going to be 5 times 6, which is 30. Now we know for part C, the velocity of the ping pong ball. Well, the momentum of the ping pong ball is the momentum of the bowling ball, which is 30. So here we go. 30 equals the mass of the ping pong ball times its velocity. So we've got 30 equals, and the mass of the ping pong ball is 0.01, which is v of the bowling ball. So we end up getting, is that right? Let me double check. 30, that's 5 times 6. Okay. We're getting 3,000 meters per second is the velocity of the ping pong ball. I want to be clear on this. You're going to be able to stop the ping pong ball just like you're going to be able to stop the bowling ball. I just think that at 3,000 meters per second, the way you're going to stop it in the same time is that it's going to punch its way through your organs. Just my idea. I could be wrong. I've been wrong before. Question number 5. Explain using momentum and impulse why your egg drop basket kept the egg from breaking, but dropping on the ground smashes the egg. And let's explain one thing here. So let's take our egg, one here, and let's say it hits the ground. Oh, so sad. There you get the egg. Oh, it's broken. Look at that. Ugh, just awful. Just, oh, look at all that egg yolk so poor egg. And now we have the other situation. We have the egg. Go a little closer. We have the egg. The floor. And now we have like a little egg basket catcher thing. So it lands nice and happy. Now let's be clear. For situation 1 and situation 2. 1 is the ground. 2 is the basket. So we hit the ground. We know the impulse from the ground is the same as the impulse from the basket catcher thingy, whatever you want to call that. Okay. So for the ground, we have a large force acting over a small time. So the impulse is the same, but the large force over a small time destroys the egg. With the basket catcher thing, we have a small force over a large time. So impulse is the same. Impulse is the same because the egg is brought to rest in the same. The egg is brought to rest by in both situations. It's brought to rest having started at the same speed, or rather having landed at the same speed. So the impulse is the same because you have m times v from each brought to rest, and it's the same m and the same v. So we get a small force over large time, impulse is the same, so we have a small little f and a very large time. So the small force over a large time preserves the egg. Now, how do we know they land at the same speed? Okay, how do we know we have the same impulse if we drop from the same height? So, the same height implies the same speed at the ground. Since the eggs are identical, same speed times same mass equals same momentum, and the final momentum equals 0, so we have the same change in momentum for each egg, and therefore, using some math terminology, the same impulse.